Hello, everybody. This session is on AS Practicals, Unit 1, Practicals 4, 5, and 6. Previously, last year, I did Practicals 1, 2, and 3 for Unit 1, and next session, I'll go on to Electrical Practicals for Unit 2. So, Unit 4, if I can now switch my mode on my laptop. Okay, so Unit 4, Practical 4, is all about exploring Newton's second law. And as we know, Newton's second law is F equals ma. But they've got a strange expression there relating mg to m plus m a. And I think, first of all, we need to relate that to Newton's second law. So they've got this setup of a linear air track and the slotted mass m providing the accelerating force given by the little mass g to give you the force required to accelerate the larger mass. But the mass and the little mass, the bigger mass of the rider and the little mass of the slotted mass, is the total mass of the system. And so that gives you the mass of the system, m plus m. All right, and that times by acceleration gives you the resultant force, which is mg. So you can see how they've got that expression mg equals m plus m times by acceleration. Now, in order to kind of like get any graphical analysis out of this, we have to kind of like figure out what we're changing, what we're measuring, and put it to y equals mx plus c. So they are asking you to attach 5 slotted 5-gram masses to the other end. And as you add more and more masses, the acceleration will change. So, we're changing the little mass m. We're fixing the rider, big M, but the little m gets changed because the resultant force gets changed, and therefore the acceleration changes. So we have it in our format of y equals mx, where we are going to change the resultant force acting on the trolley, and we are going to measure our acceleration. So the easiest thing here would be to plot a graph of resultant force equals mg against x, which is our acceleration. So that's our x-axis, that's our y-axis, because we've related that equation to y equals mx. Now, in theory, there's no plus c, there's no y-intercept, but we don't need to kind of like force it through the origin or anything. Just be aware that it should be close to the origin and that c, the y-intercept, will be close to 0. And then the straight line going through the middle, the gradient. Now, this is a little bit confusing because the gradient m is going to be equal to the mass of the total system, big M plus little m. So it's unfortunate that the gradient symbol is also m. So not to be confused, those two little m's there, one is for the gradient and one is for the mass. So once we've got our gradient is given by dy by dx. Make sure you choose a triangle large enough so that you can get a more accurate value of what that gradient is and hence the mass of the system. So this candidate here, all right, has related y equals mx. noted that C here should be equal to or close to 0. And they've changed their masses and converted their mass in grams into newtons. Okay, so first of all, divide by 1,000 to get it into kilograms, and then times it by 9.8 to get it into newtons. So divide by 1,000, if you've got it in grams to start with, get it into kilograms, and then times it by 9.81. And you would be forgiven here if you just times it by 10, because, just for this experimental setup. Okay, so we've got a nice set of results there. We've considered that our units of our results, we put those into brackets, and we've measured the acceleration using the light gates and set up to a data logger so that we can work out what the acceleration is straight away. And then we've gone on to plot resultant force against the acceleration. And this person has got really quite a good line of best fit. We've got 1, 2, 3, 4, 5, 6. WJC minimum number of points is usually 5, but 6 is a good number in case we have an anomalous result that we either have to check again or ignore from our line of best fit. And so we've got 6 results there. We've taken a really big triangle to calculate our gradient M and to take into account any kind of scale powers of 10 to get a final mass. They've got their 0.187 by taking the 2 dy by dx, and then take away the mass added from that to get the total mass of the rider. Okay, because don't forget that the gradient signifies m plus m. So if you take away the little m, you'll get the mass of the rider itself. Okay, so that they've done beautiful shown regular axes on both scales. They've labeled up the axes accordingly. They've put their units in, and they've used the whole graph grid available. So the scoring marks for the graph there will be high. Now, don't forget, you do get tested on practical technique in your theory papers. It's a case of, not just because you don't have an experimental kind of exam at the end of AS, you are still expected to be able to get your marks by doing good graph skills, doing big gradients to work out your big triangles to work out your gradient, your plotting of points. All of that can still be assessed in the theory papers. And I think some people forget this. Okay, right, let's move on to experiment number 5. Experiment number 5 is all about determining the Young's modulus. Sometimes we say big E for Young's modulus, or you can see it as big Y little m for Young's modulus, or just big Y on its own. All right, i.e. the stiffness of a metal, taking into consideration dimensions of that material, and it is a constant for that particular material and can be checked in data booklets. Okay, so we have here stress E equals stress divided by strain. But we know that stress is equal to force divided by cross-sectional area A, and we know extension is equal to strain, is equal to extension divided by, and they've given extension as x. I tend to use little e divided by the original length. But because you are dividing a fraction by a fraction, the second part of that division, this bit, we can turn it into a times by flipping those two over. So we get E equals F divided by A times by, flip them upside down, L naught divided by extension X or little e. And if you use little e, it'll spell flee, F-L-A-E, to remind you that that is the expression for the Young's modulus. Okay, so now what we need to do is relate this to some sort of y equals mx plus c so that we can plot a graph and vary some things. So the obvious choice, and I've done this two different ways, they have set up a device from the ceiling and they've measured the extension as you change this variable load here. So this is your load F here. From, you can use mg, the mass in grams, times by, or divide by 1,000 and times by 9.81 to get it into a load F, which is measured in newtons, okay? Because you probably have little masses on, but you don't know what the load is, so you have to convert from grams into newtons to make it into a load. And this is what you're going to change. So you're changing the loads and you are measuring the extension on the vernier arrangement. Now, usually how vernier arrangement works is you take a reading at one level, make sure the level, spirit level, is level at that initial reading, add an 1 Newton load, and then take the new reading of the vernier scale, and then you take away those two readings in order to work out the extension. Now, we don't have this system in our school, so we used a method of clamping a copper wire at one end of a table, putting a couple of tables along, putting a pulley onto the table so that we could hang this load F here. And we used a traveling microscope in order to read off the vernier scale. When we put a little bit of a Tipex mark on the copper wire, we took the reading, you know, we put 1 Newtons on just to make sure it was all straight, and then we put another Newton on. Difference in the vernier reading was the extension when you apply a load. Okay, so what we need to do is we need to kind of relate our expression of E equals F A L naught over extension X. You can see that this candidate has used E for X, that's fine, little e. And then rearrange it so that you've got the force isolated on its own. So F equals E A X over L naught. And I'm just going to flip it over then. So F equals E A L naught times by X. And Y is what we change. And M is the gradient. And X here so happens to also be X, or it could be little e, the extension. And that tells me that if I plot the force against the extension here, X, on the Y against X graph, then the gradient, little m, the gradient, is going to be equal to the Young's modulus, E, times by the cross-sectional area, A, divided by the original length. Seems to be a lot here, but what we can't do is just take 1 point and put it into the equation to get E. And you'd think, well, why not? We do have to kind of like take readings for different values and to present a graph so that the points you can see whether they're close to the line of best fit or not. So this candidate here has got a set of readings. We don't just satisfy ourselves with just putting 1 point into an equation to get Young's modulus out. We try and get a range of readings. We're now physicists, so this is what you're expected to be able to do. Get a range of readings, plot your graph, get your line of best fit, and from that, the points might be on the line, they might be off the line. You are going to get a more accurate set of calculation to get your E. So looking at this, if we put F, and don't forget the units of F in newtons, against extension, okay, along here, you can either use E or X, and remember extension in millimeters here that we've measured, so we're going to have to take into account of that. So it's going to be easier to put times 10 to the minus 3 to get it into meters, and not just leave it in millimeters, because you need to consider the units need to be kind of SI units in order to get your Young's modulus out. And Young's modulus is in newtons per meter squared. The area, to get the area, that's the cross-sectional area of the wire that you're using, you'd have to measure the diameter of using a micrometer screw gauge, and you can do this to get your diameter and then substitute that in by getting from your diameter, you can divide that by 2 to get your radius, and then the cross-sectional area will be given by pi r squared. If you wanted to work in diameters, you could, because you can just say pi equals pi times by d squared over 4, because diameter over 2 is the radius, so diameter over d squared over 2 squared would be the radius squared, so that's pi d squared over 4. You can do it like that. And the original length you would measure with a ruler, and you have to kind of like watch the precision of these, because a micrometer screw gauge, if you're using a manual screw gauge, is plus or minus 0.1 of a millimeter. Okay, if you're using a digital one, then it's plus or minus 0.01 of a millimeter, whereas a ruler will be plus or minus to the nearest millimeter. So you can measure the ruler of the whole length of the wire from the clamp all the way through to where it joins with the weight. So you can see that even when we've plotted our graph and choose sensible scales, make sure that you spread it out over the half of the grid available. So in this case, I've got load going up to 7, 1, 0, 1, 2, 3, 4, 5, 6, 7. That wouldn't be good enough here, because I can stretch that scale 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14 to give double the scale. So what I should be doing is, and if I do it in a different color, just a green, let's have green, it'll be 0, 1, 2, 3, 4, 5, 6, 7. Make it regular. Okay, that bottom one, that goes up to about 6.88. So make it regular. And I think we can get away with here 0, 1, 2. So let's take it back to red. 0, 1, 2, 3, 4, 5, 6, 7. Okay, and that's over half of the graph grid available. And then when you're plotting your points, say 1 to 0.5, 1 to 0.55, plot it to the nearest half a square. 2 to 1.05, 2 to 1.05, that's halfway in between one square. So you can see where this is going. I'm worried that it's quite a, maybe there's something, it should be a straight line. So let's just have a look where 7 goes, 6.88. 7 goes to 6.88, so 7 goes to 6.88 there. Okay, 6 goes to 5.53, 5.53, oh, it's looking okay. 4 to 2.65, no, 5 to 3.5 to 3.56 there. 4 to 2.65 there. Oh, probably a little bit more than half a square off there, and 3 to 2 here. That's not looking too bad, not looking the best, but if I am going to do a straight line, let's just see if I can do a straight line. Now you're going to have a clear plastic ruler on this, and when you put your clear plastic ruler, kind of run it so you've got an equal distribution of points either side of the line along the whole length of the line. So I'm just going to have a good old go here, but of course mine is freehand, yours won't be like this. So I'm going to go okay, like that. Right, now just make sure that you use a ruler and a sharp pencil. Don't do what I've done and do it freehand. Do use a ruler. But you can see that I've got like 1, 2, 3 below the line, and I've got 2 above the line, and I've got a couple on the line. So that's a reasonable line of best fit. And then when you kind of like draw your, I'll do it in green so it's a different color, your triangle, in order to get, just make it as big as possible. All right, just make it as big as possible, and do the read-offs and show the read-offs actually onto the graph. Okay, so this one goes up to 2.2 here, this one up to 7 here, this one is 6.5 here, and this one here is probably 0.1 here. So when you do your dy by dx, and again, you will be expected to be able to plot a graph in the theory paper, be it Unit 1 or Unit 2, with a set of data that they've given you. So it is important to try and get it to the nearest half a small square, regular scales, label axes, remember units, all of the things that you've probably been taught, but you just have to slow yourself right down and make sure that you do it as you go along. So dy by dx is 7, take away 2.2, divided by 6.5. Always show you're working like this. Okay, and I'll have a look what that comes out. Now don't forget, on the bottom there, it's times 10 to the minus 3 here. Okay, so once you've got your value of your gradient, m, all right, that will be equal to EA over L naught. So you've measured your diameter, you've calculated your area, cross-sectional area, you've measured your length. So now we can rearrange this. M times L naught over cross-sectional area gives you the Young's modulus. Okay. And provided that you've converted everything so that, for example, your micrometer screw gauge gives you a reading of plus or minus 0.1 millimeters. So make sure that before you put that reading of the diameter and divide it by 2, you take forward the conversion into meters, i.e. that's going to be times 10 to the minus 3. And it should come out as a very, very big numbers for this Young's modulus. This Young's modulus being for copper, it'll be in the order of like 10 to the 7. So this cross-sectional area should be very small, because 10 to the minus 3 squared, and it's going to be a very small diameter, it's going to be 10 to the minus 6. At least, because you're going to square the 10 to the minus 3 to get 10 to the minus 6. So it will come out, and it will come out big, and that Young's modulus will be newtons per meter squared. All right, stick to SI unit, convert as you go along, and watch this. All right. Okay, I think moving on now from our Young's modulus, that's probably the most complicated. You might not have, addressed materials just yet in the syllabus. You will do towards the end, and you will be expected to work out what the Young's modulus is. You'll be expected to know kind of like what instruments you're using to measure everything, what you have to measure, what the position is, i.e. the resolution of the equipment in this case, and then how you're going to manipulate those results on the graph to get a graph, to get a gradient, to get a Young's modulus. And you can see it's quite involved and detailed, but that skill of relating y equals mx, and in this case, c plus c is 0, but I haven't forced it through the origin. We just know that it should be close to the origin, but we're not forcing anything through the origin because there could be a systematic error. Okay, let's go on to the final experiment for today, and that is the force extension relationship for a rubber. So experiment 6, let's change the color, experiment 6 in unit 1. And this is the only graph that I have come across in your unit 1 and your unit 2 experiments where you are going to get a curved trend here of some sort, because you will know when you study materials is that for brittle materials will show a straight line with a Young's modulus. For example, glass, it will have force against extension as a straight line. Whereas if you kind of like look at ductile materials, i.e. it's got a plastic part, then the force against extension graph is straight for the first part and then it curves off. Now sometimes you'll see a little dip, or sometimes you'll just see it level off until fracture, and that's because of necking effect. But it's a curved trend there. But we can get the Young's modulus on the initial first bit, and likewise for the rubber, what we are going to expect is force against extension. We are going to expect something that looks like this on loading, and then on unloading it kind of comes back to the origin, so force against extension. So basically we can set up so that you've got a rubber band, and put that rubber band, cut it so that you've only got one section of the rubber band, and you can hold it at the top and attach 50-gram masses to a mass holder to vary the force acting. All right. Now you'll have to convert what you add in grams to force. You know how to do that now. If you've got grams, divide it by 1,000 to get it into kilograms, times it by 9.81 to get it into newtons. And all you have been asked to do is to plot a force extension graph. So force against extension. Now this extension here is in centimeters, I think. Let's have a look. Yes, so force against extension in centimeters. So we took the original length of the rubber band, we set up a ruler next to it, we clamped it, and we just measured the whole length of the ruler, of the rubber band, having cut it so that it's only a single strand. And then we loaded it up with different weights, and we measured the new length. And to work out the extension, we just took the original length, the original length here being 12, we should have written that as 12.0, because with a ruler we can measure to the nearest 1 millimeter, 0.1 of a centimeter. And we took that away then from all of the lengths to get the extension. And so if you don't do that, then you are going to have a graph that doesn't start at the origin. If you forget to take off the original length and you plot force against the length, then you don't start your kind of graph until much later on in the graph, and it doesn't go through 0 for no load, no extension. So do make sure that you're plotting force against extension and not the length of the band. So this is one that this candidate has produced, this graph, and it asks to determine the Young's modulus from the linear section. Now, to me, the linear section would be the first part. Now, if we relate it to this graph here first, it'll be this part here, okay, on loading. All right, so you really do need to take that first section and draw a straight line for that first section. That's the only thing that you can relate to Young's modulus, because then it kind of stretches non-linearly. And even though it's like a non-uniform, it will return back to 0 when the load has been removed. But for the sake of this experiment and what WJC are asking, they're asking you to look at that first section. So I'm in two minds of just taking this part here or just taking that first part here. And I think what I'm going to do is I'm going to take that whole part there. So I'm going to make it red. I haven't got a ruler, but you will have a ruler, and you can get a ruler to that first part and then get a large enough gradient then. I'll do the gradient in green. All right. And then somehow we've got to relate that section. Okay, dy by dx is equal to m, the gradient. But we've already know how to do this because we had force extension before, and our m before is dy by dx is equal to, let me just relate back, EA over L naught, EA over L naught. So what you're going to have to do is take your original length, that was 12 centimeters, so 12.0 centimeters times by 10 to the minus 2. Area, now you're going to have to get the cross-sectional area of your rubber band piece. So if you've got your rubber band here and you've cut it in half, all right, we'll only have the one layer. You're going to have to measure this thickness here, T, and you're going to have to measure this width here, W. And the best way of doing that is by either a vernier scale, a vernier caliper, or a micrometer screw gauge. Now, you can use any of those two. The problem is with the micrometer screw gauge is that you will squash the rubber band. So it might be better to use a vernier caliper here, which has got kind of like a little bit wider teeth. But it means that it's not as precise, because the vernier caliper can read to the nearest 0.1 of a millimeter. Have I got that wrong on that one? What did I say for the vernier caliper? And the micrometer screw gauge, 0.1. 0.1. So the vernier caliper. So what I've got this wrong. So this should be 0 plus or minus 0.01 of a millimeter for micrometer screw gauge. And if you've got a digital one, it'll go, you know, even more precise, 0.001 of a millimeter. Whereas a vernier caliper can read to the nearest 0.1 of a millimeter. The ruler is to 1 millimeter. That's how you can remember it. Ruler, plus or minus 1 millimeter. All right, because you can see the millimeter graduations. A vernier caliper goes 10 degrees more precise, i.e. plus or minus 0.1 of a millimeter. That's a manual one. But if you have a digital one, it will go to 0.01 of a millimeter. And then the micrometer screw gauge is plus or minus 0.01 of a millimeter. But a digital one will be 10 times more precise to have a higher resolution of plus or minus 0.001 of a millimeter. Confused? But to be honest, as long as you're not using a ruler here, okay, because the ruler is only 1 millimeter. And I don't think that's good enough in this particular case. So once you've got your thickness and your width in to the nearest, say you used a vernier caliper and it was, say, 2.7 millimeters thickness, and the width was, say, 8.0 millimeters wide, then to work out the cross-sectional area, you do W times by T. But you can see there that I have got it all in millimeters. So it's going to be much easier to convert into meters. So A equals 8.0 times 10 to the minus 3 times 2.7 times 10 to the minus 3 to get it into meters squared. Otherwise, you're not going to have consistent units for your Young's modulus. There's too much to go wrong, so you might as well just convert it into meters at source for the W and the T, and then times them together. I've got my L0 in meters because I converted from centimeters into meters, and so that leaves my gradient here, dy by dx. When I'm reading this off, 6, 0, and 31, because every 2 goes up in 1, 31 and 0. So if I go 6, so M is 6 take 0 divided by 31 take 0, but times by 10 to the minus 2, because I've got this in centimeters. I think that's centimeters. Okay, so then I've got my gradient now consistently, newtons per meter. And then I've got my area in meters squared and my L0 in meter. You might think, why am I going on? Because otherwise your Young's modulus value is not going to be as, it's going to be out of kilter, because the Young's modulus has a unit of Newton per meter squared. Okay, all right, so, but we can only do that for the straight part of the graph, okay? And if, you know, as an extension to this, and you might do this in your course, you will have to do the force against extension for loading, and then you can do it for unloading. And then to further this even more, you can work out another graph skill that you will need is work out the area underneath that graph. And the area underneath that graph is the amount of like energy stored in loading up, and the amount of energy stored per unit volume on unloading. So if you take the two areas away from one another, underneath the graph for loading and underneath the graph for unloading, you take them away from one another, you can work out how much energy is left inside the rubber band once you have unloaded it. And if you keep stretching a rubber band and put it to your lip, you can feel that heat energy which is stored in the from having loaded it up and unloaded it. Okay, so those are our 3 experiments for Unit 1 that I wanted to do because I didn't have enough time last time to do those. We've done Experiment 4 with Newton's second law. We've done Experiment 5 looking at materials under stress, the Young's modulus, so you'll come across that later on in your course. And Experiment 6 looking at the force extension relationship for rubber, and we just focused on the first part, the linear part, to get a Young's modulus for that part. You can't do it later on. What I'd like to go on to is kind of like looking at electrical experiments next time, and looking at what you will develop in terms of your graph skills, in terms of eventually drawing kind of like error bars. So this is something for next year, really, working out uncertainties and working out kind of like where those uncertainties are plotted. And then from those uncertainties that you plot, having plotted the points and put the error bars on top of those points, then establishing what we call lines of worst fit. So all of this year, all of your graphs will be lines of best fit. But next year, you will develop skills to draw lines of worst fit, where you can get a minimum gradient and a maximum gradient. So you're not going to draw 3 lines. You just won't draw your line of best fit. You'll be drawing your 2 lines of worst fit. Okay, but that's something to consider for again. And next time I'll be looking at the electricity unit and the first 3 practicals that we need there. I hope you got something out of this, and I'll see you all next time.